Imagine you have two identical sets of chemical building blocks, like the exact same atoms, the exact same number of bonds.
Right. And one of those structures happens to be this wildly famous, highly effective cure for testicular cancer.
Yeah, and the other one, it does absolutely nothing, completely useless in the human body.
It's wild. The only difference between life and death is literally just how those identical pieces are arranged in three-dimensional space.
Which, I mean, it completely shatters those rigid rules that your students spend their entire first few terms of general chemistry learning.
Oh, absolutely. They get so used to the octet rule and simple VSEPR geometries, and then you introduce transition metals, and it feels like the fundamental laws of chemistry are just, well, they're bending.
Exactly. And that is exactly why we're dedicating this deep dive to Chapter 22 of Julia Burge's textbook on coordination chemistry.
So we are speaking directly to you today, our listener. We know you're a community college chemistry professor out in Oregon.
Yep, staring down the barrel of your spring term, getting that general chemistry, Adam's first course, ready to go.
And look, because you already know the science inside and out, we're not just going to read the textbook back to you.
Right, no basic oxidation math today. Think of us as your peer-to-peer sounding board.
We want to analyze the content, figure out exactly where your community college students are going to hit a cognitive wall, and really brainstorm some pedagogical strategies.
Strategies to make these highly abstract concepts actually stick. So let's start with the foundation.
Yeah, because before your students can appreciate cancer-curing geometries or, those brilliant neon colors, they need a mental model.
Right. What is the anatomy of a complex? They really have to understand Alfred Werner's coordination theory.
Which is a great opportunity to bring in some chemical history. I mean, Werner proposed this in 1893. He was, what, 26 years old?
Just 26. Yeah, and the historical context is such a fantastic pedagogical tool here.
It really is. Werner was looking at compounds like cobalt-3 chloride reacting with ammonia.
But according to the standard valence theory at the time, the late 19th century rules, both of those molecules were totally satisfied.
Right, their valences were full. They technically had no business reacting with each other.
None at all. Yet they formed this highly stable, brightly colored compound.
And he had no X-ray crystallography to actually look at the molecules.
Right. None of our modern tools. He had to deduce the entire 3D structure using basically just conductivity measurements and precipitation reactions.
Which is a great hook for your class.
Yeah.
How exactly did he prove this theory using just precipitation?
Yeah, that sounds like the perfect critical thinking exercise to pose to a classroom.
So Werner added silver nitrate to these cobalt ammonia complexes.
Okay, because he knew silver would precipitate out the free chloride ions, right, as silver chloride.
Exactly. And depending on how much ammonia was in the complex, entirely different amounts of silver chloride precipitated out.
Oh, wow.
Yeah. And this led to his massive breakthrough. Elements actually exhibit two entirely different types of valence.
Right, the primary valence, which we now just call the oxidation state.
And the secondary valence, which is the coordination number, basically the specific number of ligands directly attached to the metal center inside that inner coordination sphere.
So the secondary valence is essentially the structural architecture.
Yes.
And those chloride ions that didn't precipitate, they were trapped inside that inner architectural sphere.
Exactly. They couldn't react with the silver at all, because the metal acts as a Lewis acid, accepting electrons, and the ligands are Lewis bases.
Right, donating their unshared electron pairs to form those coordinate covalent bonds.
But here's the thing. This dual nature of the valences creates a massive cognitive roadblock for students.
Oh, I see it all the time. They constantly confuse the overall charge of the complex with the oxidation state of the central metal,
All the time. They'll look at something like the hexachloroplatinate 4 ion.
which has an overall -2 charge.
Right, and they just blindly assume, oh, the central platinum atom must also be -2.
So what is the best way to untangle those two concepts in their minds?
Okay, let's unpack this. You need a highly relatable analogy, one that separates the intrinsic property of the metal from its physical attachments.
Okay.
I highly recommend teaching the bank account versus hands-held model.
I like the sound of that.
Yeah, tell your students to think of the metal's primary valence, the oxidation state, as a person's bank account balance.
Okay, so it's this underlying financial reality.
Exactly.
So in the case of hexchloroplatinate, the platinum's bank account is basically sitting at a +4.
Right. Now, the secondary valence is simply how many hands that person is holding in a crowd. That's your coordination number.
Okay, that makes sense. A neutral ligand, like an ammonia molecule or water.
That's like holding a hand with someone who doesn't affect your finances at all. They take up a spot, they hold a hand, but the bank account stays exactly the same.
But an anionic ligand, like a chloride ion, that holds a hand while simultaneously dropping a negative charge into the account.
Precisely. So if platinum's holding 6 chloride hands, those 6 negative charges pull that positive 4 bank account down.
Right down to an overall balance of -2.
Yes. Separating that spatial concept of holding hands from the mathematical concept of the bank account really helps them compartmentalize.
It totally does. And actually, while we're on the topic of ligands holding hands, this is the perfect moment to introduce polydentate ligands.
Oh, chelating agents.
Yes, because they're incredibly visual. Tell your students that the word chelate actually comes from the Greek word chele.
Which means claw, right?
Exactly. So a beadentate or polydentate ligand doesn't just hold one hand, it literally wraps around the metal ion like a lobster claw.
And the classic example in the Burge text is EDTA, right? Ethylene-dimetresidate.
Yep, EDTA. It has 6 donor atoms. It completely engulfs the metal ion in this like hexadentate grip.
That's such a great visual. When students picture a microscopic claw aggressively grabbing onto a metal ion, they grasp the stability of those complexes so much faster.
Far better than if you just, read them the dry textbook definition.
Definitely. So once they grasp that central anatomy, the metal bank account surrounded by ligand hands and claws, what's the next cognitive leap?
Well, the next leap is realizing that simply rotating those exact same pieces in 3D space creates fundamentally different substances.
Stereoisomerism, where chemistry effectively becomes architecture.
Exactly. We're mainly dealing with geometric isomers here, like cis and trans configurations, and optical isomers, the enantiomers.
I can easily see a student looking at the cis and trans isomers of diamantochloroplatinum-2 on a whiteboard and just thinking they're rotated versions of the same toy.
Right. They have the same platinum center, 2 ammonias, 2 chlorides. How do you convince a skeptical student that this spatial difference actually matters in the real world?
Okay, this is where you deploy the cancer drug hook we open with. You have to tell them the story of Barnett Rosenberg in the 1960s.
Oh, the biophysicist.
Yeah, he was running an electrical current through platinum electrodes in a solution of E. coli bacteria.
And he noticed the bacteria just stopped dividing, right? They grew into these massive, long filaments instead.
Exactly. He accidentally synthesized a platinum coordination complex using the electrodes and the ammonium chloride buffer in his solution.
But the crucial part of this story for your students is the geometry.
Yes. Rosenberg discovered it was specifically the cis isomer that caused this dramatic biological effect.
Because in the cis configuration, those 2 chloride ligands are sitting right next to each other on the exact same side of the platinum atom.
Right. And because of that very specific geometry, the molecule perfectly fits into the major groove of DNA.
It binds to the guanine bases and physically prevents the DNA strands from separating.
Which completely stops cancer cells from replicating.
Wow. So that is cisplatin, the famous chemotherapy drug. But what about the trans isomer?
Well, the trans isomer has the chloride ligands on opposite sides.
Yeah.
So it physically cannot cross-link the DNA in the same way.
It doesn't fit.
It doesn't fit. It is completely biologically inactive. Same atoms, same bonds, entirely different biological destiny based purely on a 90-degree shift in geometry.
That is wild. That immediately takes it from a dry textbook diagram to like a high-stakes life-or-death reality.
Exactly.
So that covers the geometric isomers really nicely. But optical isomers always feel much more abstract.
Yeah, they do.
How do you ground the concept of chiral molecules in non-superimposable mirror images?
Well, the classic left-hand versus right-hand physical demonstration is essential here. Just have your students hold up both hands.
Okay, they're perfect mirror images.
Right. But if you try to lay your left hand perfectly flat over your right hand, with the palms facing the same direction.
The thumbs stick out on completely opposite sides.
Exactly. They are non-superimposable. That is chirality in a nutshell.
But, I mean, hands are easy to see. Molecules have identical boiling points, identical densities, identical colors.
Yeah, they look exactly the same on paper.
So how do we actually prove to the students that these microscopic chiral isomers are interacting with the universe differently?
You introduce the polarimeter. You explain that this 3D twisting interacts differently with plane polarized light.
Okay, so if you pass a beam of light that is vibrating in only one plane through a solution of one chiral isomer,
the physical asymmetry of the molecules rotates the light to the right, We call it dextrorotatory.
And if you pass that same light through a solution of the exact opposite mirror image, it rotates the light the exact same amount to the left.
The literotatory isomer.
Right. So it's physical proof that this spatial architecture dictates how the molecule physically twists the electromagnetic field around it.
It's amazing how this 3D geometry dictates everything. Its biological destiny, its interaction with polarized light.
But you know, that spatial arrangement does more than just fit into DNA or twist light beams.
Oh, yeah.
Yeah, it actively dictates how the transition metal interacts with visible light on a quantum level.
Which brings us to the most visually striking part of the general chemistry lab.
The brilliant neon colors of transition metal complexes. Here's where it gets really interesting.
Yes, this is the realm of crystal field theory, or CFT.
And it's an incredibly elegant model because it strips away all that complex orbital hybridization.
Right. It treats the entire interaction purely as electrostatic forces.
We know the positively charged metal attracts the negatively charged ligands, but CFT asks the students to focus on the repulsion.
Exactly. Because the transition metal already has its own d electrons occupying space around it.
And the incoming ligands are bringing their own lone pairs of electrons to form the bonds.
And as we know, electrons violently repel other electrons.
Yeah, but bridging that gap between electrostatic repulsion and the actual splitting of the orbitals, that can lose a lot of students.
Oh, definitely. You need a visual analogy that explains why some orbitals go up in energy while others go down.
So what's the best pedagogical approach for visualizing that split?
I always recommend the crowded elevator analogy.
Okay, I'm listening.
Have your students picture the 5 dative orbitals on the central transition metal as a spacious elevator. Initially, all the electrons in that elevator are on the exact same energy level.
They're degenerate. Everyone is totally relaxed.
Right. Then the doors open, and 6 new passengers, the ligands, aggressively push their way in to form an octahedral complex.
And because of the physical geometry of the ligands approaching along the X, Y, and Z axes, they're pushing directly into specific areas of the elevator.
Yes. The electrons that happen to be standing in the orbitals pointing directly at the doors, they get completely squished by the incoming ligands.
So their electrostatic stress levels shoot up, which means their energy levels shoot up.
Exactly. Those become the 2 higher energy orbitals.
But what about the electrons in the orbitals that point between the axes?
Well, they're the people hiding in the corners of the elevator. They avoid the direct pushing.
Okay, so because the overall space is now crowded, they're still under some stress, right?
Right, but relative to the squished electrons at the doors, their energy level is significantly lower. So the 5 Dürr orbitals have now split into 2 distinct energy tiers.
And the gap between the squished electrons and the corner electrons, that's the crystal field splitting energy, delta.
And this is where we connect the architecture back to the colors.
Because the magnitude of that energy gap, delta, perfectly matches the energy of a specific photon of visible light.
Exactly. When white light hits the solution, an electron in the lower tier absorbs a photon with the exact energy it needs to jump across the gap to the higher tier.
But this brings up a massive misconception that plagues even advanced chemistry students.
Oh, I know exactly what you're going to say.
Right. If they're looking at a beaker of hydrated cupric ions and the solution appears vivid blue.
They will almost universally write on their exam that the complex absorbs blue light.
Yes. It is a profound, deeply ingrained cognitive bias. They just assume what they see is what is absorbed.
You have to explicitly intervene here. You have to teach the color wheel concept.
How do you frame it so it actually sticks?
You have to emphasize that the color we perceive is basically the leftovers.
The leftovers.
Yeah. If a complex uses a specific wavelength of light as fuel to make that electron jump, that color is consumed. It's removed from the spectrum.
So our eyes see the complementary color that is transmitted or reflected back at us.
Right. So for the cupric ion, the delta gap perfectly matches a photon of orange light.
The complex consumes the orange light to fuel the jump, meaning the orange is essentially subtracted from the white light entering the beaker.
And because orange is absorbed, the remaining light transmitted through the beaker hits our retinas as blue.
Orange is absorbed, blue is transmitted. It really requires constant repetition in the classroom to break that initial intuition.
It does. And the size of that gap also depends heavily on the specific ligands entering the elevator.
Which introduces the spectrochemical series, because some ligands just push harder than others.
Exactly. The spectrochemical series ranks ligands by their field strength. Weak field ligands, like water or chloride ions, are polite passengers.
They don't push very well.
Right, so the energy gap between the upper and lower orbitals remains relatively small.
But strong field ligands like cyanide or carbon monoxide, they are incredibly aggressive.
They push violently, creating a massive energy gap.
And that gap size dictates the magnetic properties of the complex. It forces the electrons to make a literal cost-benefit analysis.
It really is a thermodynamic trade-off. I mean, electrons naturally want to spread out and avoid pairing up because of their inherent repulsion.
So if the gap is small, created by those polite weak field ligands, it costs less energy for an electron to jump to the upper tier than it does to share an orbital.
Which results in a high-spin complex. You get a maximum number of unpaired electrons, making it highly paramagnetic.
But if you have strong field ligands, that delta gap is gigantic.
Huge. An electron looking at that jump realizes it takes far too much energy to reach the upper tier.
So it reluctantly accepts the lesser penalty of pairing up in the lower tier.
Exactly, yielding a low-spin complex with fewer unpaired electrons and weaker magnetic properties.
It is just a beautiful example of molecules behaving purely based on energy minimization.
Absolutely.
So we have the static architecture, the spatial twisting, the electron splitting, and the colors all mapped out.
But chemistry doesn't just sit in a beaker looking pretty.
No, it reacts over time. Which brings us to the final major hurdle of Chapter 22.
The lability versus stability paradox.
Yes. If we connect this to the bigger picture, this is where you have to untangle kinetics from thermodynamics.
The textbook uses the hexamine cobalt 3 complex as an example.
Right. It states that in an acidic solution, this complex is highly thermodynamically unstable.
The equilibrium constant dictates it should react and change completely. Yet it takes days for the reaction to occur because the complex is kinetically inert.
So how do you explain to a student that something can be totally unstable but simultaneously inert?
You have to separate the destination from the journey. Thermodynamics tells us about the destination.
Is the final product at a lower, more comfortable energy state than the starting material?
Right. If, yes, the starting material is thermodynamically unstable, it fundamentally wants to reach that lower state.
But kinetics is the journey to get there.
Exactly. I always recommend using the analogy of a massive boulder sitting at the very peak of a tall mountain.
Okay, so because of gravity, that boulder is in a highly unstable state. It's thermodynamically driven to reach the bottom of the valley.
But if that boulder is resting at the bottom of a 10-foot deep crater at the top of that mountain, it isn't going anywhere on its own.
Ah, that crater represents the activation energy.
Yes, the boulder is kinetically inert.
Yeah.
Even though it is thermodynamically unstable and wants to be in the valley, it requires a massive influx of energy
A huge push.
just to get out of the crater before it can roll down the hill. For the cobalt complex, the activation energy required to break those strong cobalt-nitrogen bonds is so incredibly high that the reaction happens at a glacial pace.
Even despite the favorable thermodynamics, that's a great analogy.
And a Labol complex is the exact opposite.
Like the tetracyanocolate 2 ion, it's thermodynamically stable, sitting securely at the bottom of the valley.
But if you introduce radioactive cyanide ions into the solution, they swap out with the existing ligands almost instantaneously.
Because the kinetic barrier, the lip of the crater, is practically non-existent.
The bonds can break and reform rapidly with very little activation energy, making it highly labile, even while the overall complex maintains its stable thermodynamic baseline.
To really cement this lability versus stability concept, though, your students need a killer real-world application.
Oh, and the Burge text provides a fantastic one with chelation therapy for heavy metal poisoning.
It perfectly synthesizes the entire chapter. Lead poisoning is a tragic reality.
Often from degrading paint in older homes or contaminated water pipes.
And when lead ions enter the bloodstream, they're highly toxic because they act as stronger Lewis acids than the metals naturally present in our enzymes, like zinc.
The lead essentially hijacks the enzyme. It forms coordinate covalent bonds with the sulfur and oxygen atoms in the protein structure, shutting down the central nervous system.
So the biological problem is that lead is forming these devastating coordination complexes inside our bodies.
Right. So how do doctors use thermodynamics to get it out?
They administer EDTA, the hexadentate claw we discussed earlier.
Yes. EDTA has a massive formation constant with lead. It forms a complex that is incredibly thermodynamically stable.
far more stable than the bonds the lead has formed with the patient's enzymes.
So it's essentially outcompeting the proteins for the lead ion. It drags the boulder into an even deeper thermodynamic valley.
Wow. The EDTA wraps its 6 donor atoms around the lead, ripping it away from the enzymes.
And crucially, this new EDTA lead complex is highly water-soluble.
Because the claw refuses to let go, the heavy metal is safely transported through the bloodstream and excreted by the kidneys.
Thermodynamics literally saves the patient's life.
But the textbook also highlights the dark side of this thermodynamic power, right? With polyphosphate detergents.
It's a very sobering ecological counterexample. Decades ago, detergent manufacturers used sodium tripolyphosphate as a builder in soap.
It's a powerful chelating agent that grabs onto calcium and magnesium ions in hard water, preventing soap scum.
From a pure chemistry perspective, it was a thermodynamically brilliant solution.
But ecologically, it was a total disaster. Those highly stable phosphate complexes wash down our drains and into lakes and rivers.
And phosphates are a limiting nutrient for algae. So when we dumped millions of tons of this chelating agent into the water supply, it acted as a super fertilizer,
causing massive algal blooms. When the algae inevitably died, the bacteria decomposing them consumed all the dissolved oxygen in the water,
suffocating entire aquatic ecosystems. It's a process called eutrophication.
It's such a powerful lesson for students that a deep understanding of coordination chemistry isn't just an academic exercise.
No, it has profound implications for public health and environmental policy.
So as you prepare to stand in front of your spring term students, you have a really solid pedagogical roadmap.
You can walk them through Werner's ingenious deduction of primary and secondary valences using the bank account and hands analogy to keep the math straight.
You can ground the abstract spatial reasoning of geometric and optical isomers in the very real, very high-stakes history of the cisplatin cancer discovery.
You can tackle crystal field theory and the origin of color by putting those d electrons in a crowded elevator and making sure you relentlessly correct the absorbed versus transmitted color wheel misconception.
And you can solidify their grasp of lability and stability by separating the thermodynamic destination from the kinetic journey, bringing it all home with the life-saving mechanism of EDTA chelation.
It is a challenging chapter, but providing your students with the tools to visualize the invisible architecture of the universe is incredibly rewarding.
Before we wrap up, what is one final thought exercise our professor can take into the classroom to test if the students have truly internalized these concepts?
I highly suggest asking them to consider the hemoglobin in their own blood.
Oh, okay.
The iron center in hemoglobin is a coordination complex, and its primary job is to weakly bind oxygen as a ligand, so it can transport it through the body and release it.
Right.
Ask your students to predict what happens on a molecular level if they inhale carbon monoxide.
Oh, because based on the spectrochemical series, carbon monoxide is one of the strongest field ligands in existence. It pushes far harder than oxygen.
Exactly. Challenge them to trace the cascade of effects. How does that sudden, violent influx of strong field ligand change the crystal field splitting energy of the iron's d orbitals?
How does it force a transition from a high spin to a low spin state?
And ultimately, why does the resulting massive thermodynamic stability of the carboxyhemoglobin complex create a fatal kinetic trap that suffocates the body from the inside out?
That is a brilliant, terrifying synthesis of every concept in the chapter.
It really is.
It reminds the students that these shifting molecular geometries and splitting energy levels aren't just abstract rules.
They're the delicate biochemical balance keeping us alive, one coordinate covalent bond at a time.
To our listener in Oregon, thank you for your dedication to your students. Have an amazing spring term.